Here's a good demonstration on the nature of centripetal versus tangential vectors. So here's a ball on the end of a string, and note, the faster I spin it, the more horizontal the string becomes, but there's no speed for which the string will be perfectly flat and horizontal. In any case, right now, I'm spinning the ball around with a constant speed, right? So this represents uniform circular motion. Now, even though the speed is constant, the ball is still accelerating, and that might conflict with your definition of acceleration. You might think of acceleration as strictly a change in speed, but it turns out acceleration is a change in velocity, and velocity is both speed and direction. So yeah, things can accelerate by changing their speed. If you drive in a straight line and step on the gas pedal, you've accelerated. I suppose even if you step on the brake pedal, you've accelerated. You've just accelerated in the negative direction. But even when you use your steering wheel, you're accelerating because you're changing the direction of your velocity vector. And any change in velocity corresponds or correlates to an acceleration. So right now, the acceleration vector at all times points exclusively toward the center of the circle. Alternatively, I could start spinning it slowly and then spin it faster and faster and faster and faster and faster. Now, in that case, the acceleration would point somewhat in the forward direction. So let's say the velocity at a snapshot in time points in this direction, and it's speeding up at the same time. Then it has a corresponding acceleration due to the change in speed that also points in the tangential direction. But you can't dismiss that at the same time, it also has an acceleration that points toward the center of the circle. There's no way for an object to go in a circular path and not have some component of acceleration that's centripetal. It may or may not have the tangential component depending on whether or not it's changing speed as it moves around the path, but it always has that centripetal component. So we can label these. This is the centripetal component to the acceleration, and this is the tangential component to the acceleration. But if the velocity, if the speed is constant, and therefore the velocity is still changing just due to the fact that it's changing direction, then this tangential component to the acceleration goes away, right? Constant speed still refers to a centripetal acceleration with no tangential component. So last thing, I want to prove to you that the acceleration is really centripetal, center-seeking, as opposed to centrifugal, center-fleeing. So you notice right here, there's a little bobber inside a glass jar. And I want to show you that the bobber always points in the direction of the acceleration. So watch this. I'm going to start from a state of rest, and I'm going to quickly speed up in this direction and then really quickly slow down so my acceleration will point back in this direction. And watch where the bobber in the jar goes. So you see, while I accelerated forward, the bobber went forward. And when I accelerated backward, it went backwards. So the bobber always points in the direction of acceleration. Let's try again going this way. From a state of rest, speed up in this direction, and then quickly slow down and accelerate back in this direction. So I predict the bobber goes forward at first, and then backwards. Let's see. Sure enough. So if I'm right, if I hold this out at arm's length and I start to spin around in a circle, I think the bobber is going to point in the direction of the acceleration toward the center. So watch and see. Sure. Hopefully you can see that. So there's a little bit about these terms, centripetal, meaning center-seeking, and tangential, meaning, well, of course, tangent to the circular path. All right, thanks for watching.